Hello, my name is Richard Self and I'm from the University of Derby. I'm going to be talking today about some of the most interesting lessons that we've learnt about big data and analytics during the last 3, 4, 5 months during the COVID-19 pandemic. What I want to do first of all, though, is to introduce myself. Well, I've been modelling in my head and I've been modelling in computing terms for the last 50 years. And I'm quite good at it, although I say it myself. I build models in my head and I build models occasionally in computers, in software, and in things like Excel. But what I'm particularly interested in is how we do this appropriately. I'm interested in governance. Governance is about doing the right thing in the right way, at the right time, to the right quality, and you can keep going adding on new terms with the word right just in front of it. Because of my background for 30 years in industry, I'm kind of interested in how do we make use of our technology so that it actually delivers business value. Not just using technology because technology is cool and got lots of lovely shiny buttons and things. I'm interested in the way that we use it to actually do things good for ourselves, for our businesses, for society. And as I do this with my students as a senior lecturer in governance of advanced and emerging technologies, one of the things I do with all of my students is to make them learn by doing research. I don't teach them answers. I get them to go look for the interesting questions. And then from that research that they then learn to do, to find the right answers in the right context, they then help me and give me some of the ideas that I use when I'm talking to people in business like you guys. What's really, really important is that we think about learning questions. Because, let's face it, the questions have not changed in 50 years in our industry, our IT industry. What keeps a chief information officer awake tonight is the same as kept them awake 20, 30, 40 years ago. So learning the questions is great and very, very important. But the answers, they change from context to context, from company to company, from department to department, from time to time. So that's why I'm so interested in being able to speak at these sorts of events. Now, about what I'm going to be talking to you. Well, it's actually quite interesting. I could have talked to you for hours and hours and hours about comparative numbers and comparative this and comparative that, all about COVID-19. But I want to distill down to 3 items, 3 facets that when I look back over my 50 years career, I can see the same ideas repeating and repeating and repeating, and we can see them so incredibly clearly as what's happening today as we try to understand what this virus has done and try to understand how we can treat it and how we can track it. So I'm going to be looking at the idea of models. I then want to think about assumptions, the things that underpin those models where we don't have data perhaps. And I want to look a little bit at the question of science and comparing it with engineering, because we've seen a very, very beautiful and very powerful example of it in the last few weeks. So the context is obviously about what we have learned about AI, about big data, about analytics, about machine learning, about all of these sort of things over the last focused 5 or 6 months. And we will start with the understanding what these things called models are all about. It's a little kind of an introduction that helps us to begin to focus our thoughts on how we think and how we understand what is going on around us. And from that, we'll then be able to distill 3 crucial lessons. Lessons that are important not just in COVID terms, but important in everything we do as we look at the world of big data, analytics, AI, machine learning. The first lesson is look out of the window. The second one is science is important. And the third lesson is engineering cannot fix problems in science. 3 focused lessons. Now, let us start with what is a model. Well, one definition of a model is that it is an abstraction of reality. It's a simplification. It's a way of reducing that complexity of reality to something that we can hold maybe in our hands or in our heads. It's something that we use for communication. But we always have to strip down the complexity and richness of reality into these tools or these mechanisms we use for communication. These things that we use on our heads for thinking, the things that we use on our computers for calculating, things that do AI, that do machine learning. All of these things have stripped down reality to a much smaller number of parameters, shall we call them, variables, relationships. That's what a model is. It's a reduction in the complexity of reality. Now, as we work with this, we need to think about the question or the statement from Count Alfred Korzybski, who created the concept, the study field of general semantics. The map is not the territory. Now, in a sense, we understand that intuitively, in one sense. You know, we look at a road atlas, a road map, and we know that that's just really, at the back of our minds, is for showing us how we can navigate from place A to place B. And we know, at the back of our minds, that the roads are much, much broader and wider in that map, in relation to each other and to distance, than actually on outside. But they're that wide so we can see them on the map. And so if you go back 20, 30 years before we had these computerized maps like Google Maps and Bing Maps, which had satellite views, photos as well, you know, we'd look at that and people say, gosh, look at England, it's covered in concrete, look at all those roads everywhere. And yet, when we go flying, we're up on 25, 30, 35,000 feet. And we look out of the window of our aircraft. And we look down on England or France or wherever we are. And we think, where's all that concrete gone? Where are the roads? And you look down and think, I can hardly see the roads. The road map is not the territory. So hold those 2 thoughts at the back of your mind and at the front of your mind. They're really important. Now, as we think about all of these, about models. Models, there are 2 sorts. There are the models we have in our heads. Because remember, what is in our heads is not reality. Reality is out there. What's in our heads is what we've heard through our ears, what we see with our eyes, touch with our fingers, smell with our nose, taste with our tongue. But that is an incredible reduction in the richness and complexity of what's out there. That's inside here. And then we have the external models, the shared, useful model we use for communicating, discussing, and finding things out. They live in computers and so on and so forth. But what we have to remember at all times is that every single model embodies and is composed of lots of assumptions and lots of reductions in that complexity. And yet sometimes we want to build a really, really complicated model. I was talking to a student of mine a few months ago, and he was talking to me about some model for assessing credit risk. And a group of enthusiastic data scientists got hold of this raw data, 150 columns or so, and they put it through to work out what is the logistic regression that actually calculates the best fit with high risk of default. And they put all 100, 150 parameters in, and they got a huge amount of stuff, and eventually it comes out and says, blah. And it was about 95% confident. An expert who had been working in the field for many years uses one parameter. A single parameter out of those 150. And it's just as accurate as that data scientist model with all 150 parameters. With lots of little tiny weighting factors, 0.5% here, 0.6% there, and 80% on this one. Occam's razor is incredibly important. Simplicity is best. So, models are not the reality. Models are what we have in our head. And if we look at that picture on the right, we have problems communicating our own internal models. And that's a problem we need to remember as well. Because I've got this reduced model in my head, and then having to regenerate some of the ideas through my voice as I talk to somebody else who's listening with other filters and other ways of abstracting from reality of what I said to build their own internal model. Is their model in their head going to be the same as my model in my head? Probably not. And it's worth remembering that as we have discussions. Now, the second aspect we need to think about in terms of models is this. All analytics, AI, machine learning is all about models based on statistics and mathematics. It's all models. We also have to think about a question that comes with that of whose model is it? Who thought it up? Are we using standard models, standard statistics? And if so, what actually was that particular statistical function intended to do? I mentioned just before on the last slide about assumptions. Well, we have to think about what are the assumptions? Is it in the structure of the model where we reduce the number of parameters dramatically to something that we can actually handle? To reduce it so we can actually fill some of the data points in within the model with numbers, because some of them we won't be able to measure. But we're looking at the structure of the model is one thing, and it could be an agent-based model or it could be a flow-type model. Who knows? But what are the assumptions in my head or in the model builder's head as they created that model structure? And then we have to think about the data. Some of the data are the assumptions that make the system work, the fundamental parameters and constraints. And some of it is the biases in the data. We know about the biases in data in all that we're doing. We know about the biases in face recognition. They can't see dark faces. They can't see black faces. We know about the biases that make our models about is someone liable to abscond if they're on bail. We know that we've seen so much evidence now that those models and the data are biased. How and why? Why were these assumptions made? Was it the person's background? Is it lack of diversity, social diversity, ethnic diversity, and all the other forms of diversity that mean that we haven't captured enough variety in what's going on? Have we actually ended up with too simple a model, like taking Occam's razor into account? Should we actually start building a few layers of complexity to make it work better? And finally, have we verified that model? Have we made sure that as we build the software, that it meets the specification? And then, have we validated it? Which really is saying, is the specification correct in relation to the world? The validation match. Have we done that? Does your model behave like the world? How do we know, and this is one of the questions, for example, is about the COVID, does it matter whether we do or don't wear masks? How far does these little droplets go? Has it actually been measured, or have we just got nice little aerodynamic models that show, well, with a square cube law of droplets, they'll go like that or they'll go somewhere else? Has it actually been checked in relation to real live measurements, visualization of these droplets? Do we actually know that our models work the same way? Now, the first lesson was look out of the window. It's absolutely vital. Don't worship your data or your model. And we've seen too much of that over the last few months. People are committed to their model. They won't look outside of the window to see what's going on. And we saw that in England at the very beginning, right here, at the beginning of these weeks here. These first few weeks. One of the groups was using a model based on Wuhan and the factors and the everything from there. And they were saying, oh, we're currently on a 6-day doubling period. In actual fact, if they had looked out of the window, they would have seen that the numbers were actually doubling every 2 or 3 days, not every 6 days. They didn't look out of the window at what was going on. They were dedicated to their model. Another example is the start date. When were the first events? When did COVID actually turn up in Europe? Well, if you look at the official dates, it's around about the back end of January 27th, 28th, 29th. And yet, when we started getting good, strong evidence that it was perhaps the 16th of November in France, or perhaps the 27th of November, where we know we had blood tests of someone who died. We had a lot of incidents of some really unpleasant coughs and so on, and headaches over Christmas. And yet, everybody knew, didn't they, because they were looking at their fixed perspective, that it didn't start in Europe until 25th, 26th, 27th of January. Because someone said, well, where are the bodies? Well, that was because their models, this model here, you see, shows lots and lots of people catching the virus. These, of course, remember at the very beginning were the people who were going into hospital. We were only testing people going into hospital. We weren't testing everybody else around. And even today, in the UK, the Pillar 2 testing is kind of over there somewhere. It's all complicated and difficult and messy. We know what's going on in the hospitals. Another area that we have a big problem with is trying to make international comparisons using the Johns Hopkins University data or the Worldometer data. We know that there's lots of numbers of people who've caught it and numbers of people who are dying and so on. And yet, the way we look at it on Worldometer or on Johns Hopkins is there's a single column called number of people who have caught it today, cumulative number, next column. Number of people died today, cumulative column. In actual fact, almost every single country will have slightly different definitions of the data that goes into that column. We shouldn't have one column, we should have up 200 columns, one for each country. In England we should have 2 columns, not one. We have one column which says number of people who caught it today. Actually, we should have at least 2, if not 3 columns. One, the people who've come into hospital because they're really feeling unwell, and we have those numbers, they're tested. We have the other component of the tested people, and that is the health workers and hospital people. We then have a third column, which is this Pillar 2, people out in the testing programs all over. If we had those 3 columns separated out rather than a single one, we would know an awful lot more. And the same would go in many parts of the world. Or should we actually not even worry about the number of people who've caught it? Should we be looking at these excess deaths? And even here is a problem, because if you look down at Peru here, I think you can see me touching it, it says 28,600 excess deaths this year. And yet, if you look on Worldometer and Johns Hopkins University, they've only had 7,000 actual deaths from COVID. What should we be looking at? And the lesson here is really, really important. If we look out of the window, try and look at reality, what actually is happening? Science is important. Too much of what we do in analytics and in machine learning and in AI is all about correlation models. Remember, it is not causation. Correlation is not causation. Science is causation, not correlation. Too many people, as we look at science, they have a narrow perspective. The experts have very narrow perspectives. And link into their model. And what we've seen over the last couple of days is an example. Everybody's been saying, well, we can track what's happened in the past by looking at antibody tests. Turns out, if you look only for antibodies, you only catch about 1 in 3 of the people who've had the virus. Another 2 people have got no antibodies, apparently, that's detectable now, but they've still got a T cell that is sensitive to cells which have the virus inside it. So maybe there's 3 times as many people who've had it. I'm not saying that it's right or it's wrong. I'm saying look out of the window, look at the science, don't go too narrow. And we have a problem that decision makers love the basis that technology, that science can do almost anything. We can land on the moon, we can go to Mars, we can send our vehicles to Mars, our satellites. We can go outside of the solar system. We can do almost anything. And yet we have discovered that BLE, this Bluetooth low energy mechanism, will not deliver a sensible, workable track and trace. This is to do with science versus engineering. Engineering says we can solve a problem, make it work. Science says, sorry, actually, you can't do it. And it turns out from research that's been done in Trinity College, in Dublin, and in the University of Derby that we've done, and someone else has done it, that actually BLE is not a suitable vehicle if you actually want to be able to calculate a risk profile of a contact. Remembering 1 minute at 1 metre equals 15 minutes at 2 metres in terms of risk of catching the virus. And so what we found is, just looking at this, here's the science. We've got about 300 data points on here measured at a real distance of 1.5 metres. And we have got ranges from, well, there's one right down here, very, very close, far too close, to around about 1 metre, all the way up to something like 5.5 metres. That's the reality of what you can do with Bluetooth. You can't get round it with engineering. If we look at the cumulative risk at a true distance of 1 metre, that is what it ought to build up with, effectively with time. And in actual fact, what happens is, as you walk around the beacon at 1.5 metres, at 1 metre, it's only one particular orientation of your phone will actually get you up to the correct level of risk. Most of the time, it's way down here. If you go to 1.5 metres, basically, you're around about 50%. And to look at again the science is this beautiful one. Someone has created a little app that measures what it thinks is the distance as it changes that phone, puts it in his back pocket facing towards the beacon, back pocket facing away, front pocket facing away on his hand. This is something that science is saying we cannot engineer a solution. The fundamental physics preclude it. So, in conclusion, models are simplifying of abstractions. All analytics, AI, machine learning is modelling in one form or another. You must understand the assumptions and the biases. You need to be able to understand the science and the technologies. And remember, verify and validate. It's crucial. The world is real. Models are, well, they're just models. They aren't the world. Some models are useful. Some models are wildly wrong. Thank you, ladies and gentlemen.